record. All right. Now, I'll make you a co-host, and that should enable you to do this. Perfect.
Perfect.
Okay, now you should be able to share your screen.
Okay. Do you see my title slide?
Yep. Looks
Cool.
good to me.
Okay. Thanks a lot for the introduction, Robbie. My name is Andrei. I'm a graduate student in the Faraon lab, and today I'm going to be talking about our work towards realizing quantum registers for single rare earth ion qubits using nuclear spins in the host crystal lattice. So the motivation for our work is really building large-scale optical quantum networks. And these typically consist of quantum nodes, which have the ability to generate, process, and store quantum information, and quantum channels typically consisting of flying photonic qubits, which can be used to interconnect these nodes. Unlike conventional classical networks, these quantum networks have the ability to distribute entanglement as a network resource. And this enables applications such as quantum key distribution, distributed quantum computing, quantum simulation, and metrology. The state of the art in this field is this 3-node network shown here on the right, which was realized using nitrogen vacancy centers in Diamond. However, it remains an outstanding challenge in the field to really build these systems up to large-scale multi-node networks. So this desire for scalability really motivates the exploration of solid-state platforms. And you can really think of these as being equivalent to kind of optically addressed spin degrees of freedom like you would see in, let's say, AMO type systems like neutral atoms or trapped ions. But really kind of, in our case, these atoms or defects come ready trapped in a crystal. And this is kind of a double-edged sword. On one hand, they inherit the noisy crystalline environment, typically consisting of fluctuating electric and magnetic fields. However, they also inherit various advantageous characteristics. So for one, the nuclear spins in these crystals can be used as a plentiful resource for these quantum nodes. And also, just by the nature of these solid-state systems, they're also readily integrated into electronic and photonic devices. The kind of prototypical example of one of these systems is the aforementioned nitrogen vacancy center in Diamond, but people explore other systems too, such as silicon vacancy centers and tin vacancy centers in Diamond, defects in silicon carbide, quantum dots, and donors in silicon. As is going to be the focus of this talk today, single rare earth ions doped into a variety of hosts. The rare earth ions are these lanthanide series atoms. So here are a few examples of different single rare earth ions with their corresponding crystalline hosts which have been investigated. And I'll be focusing on the 171 isotope of ytterbium doped into yttrium orthovanadate, the crystal structure of which is shown here on the right. All of these rare earth ion platforms really inherit kind of a common set of characteristics. So they have highly localized electronic states. They have very narrow spin and optical inhomogeneous line widths. Rare earth ions also exhibit some of the longest optical and spin coherence times in the solid state. And they also have highly radiative optical transitions. However, these transitions are typically very weak, and this makes detecting and working with single ions quite challenging. We work with this specific isotope of ytterbium because it has an effective electronic spin of 1/2 and also a nuclear spin of 1/2. And this leads to the simplest possible hyperfine energy level structure shown here on the right. At zero magnetic field, the hyperfine interaction actually mixes the electron and nuclear spins. And this leads to the yellow energy levels highlighted here having no magnetic dipole moment, and therefore all transitions connecting them are first order insensitive to magnetic field fluctuations. Essentially, they're all clock transitions. In addition to that, the site in the crystal, which the ytterbium ion substitutes into because of its symmetry, leads to no first order DC Stark shift for the optical transition. And this means that these transitions are also first order insensitive to electric field fluctuations too. So this makes this platform robust to basically both the electric and magnetic field noise in the host crystal. In bulk material, the excited state lifetime of these optical transitions is about 270 microseconds. And to enable detection of single ions, we actually fabricate photonic crystal cavities from the crystal. And by Purcell enhancement, this reduces the optical lifetime to about 2.2 microseconds. And in addition, leads to more than 99% of the ion emission coupling to the cavity mode. And this really enables us to both detect and interact with these single rare earth ions quite efficiently. So in previous work, in this paper, we demonstrated a number of key characteristics for this platform necessary for realizing simple two-node quantum networks. So first of all, we demonstrated that the optical transitions of these ions are highly stable with 1 microsecond post-selected optical Ramsey coherence times. We demonstrated ground state spin coherence times of about 30 milliseconds. I should actually mention one more thing, sorry, here. So for the rest of this talk, actually, we're going to be using this pair of energy levels here in the ground state separated by 675 megahertz as our qubit. And this transition here at 985 nanometers is going to enable us to optically read out the state of this qubit. And I'm going to be using this kind of spin down, spin up notation to identify these two qubit states. Anyway, so the spin coherence time on this qubit transition, this clock transition, is about 30 milliseconds. And in addition to that, we can perform high fidelity control of the qubit, and we can do single qubit gates with an average fidelity of about 99.98% measured using randomized benchmarking. In addition to that, we were able to initialize and read out the state of this qubit in a single shot with greater than 95% fidelity. However, critical to realizing like larger scale quantum networks with multi-node connectivity is the ability to have a secondary qubit register. And this was missing from this set of results. And this is actually going to be the focus of my talk today. Such secondary qubit registers in the solid state are typically realized using nuclear spins of the crystal lattice. And there are a range of different regimes which have been explored for this application. And I'm going to explain a few of these here. So the most studied regime consists of a very localized electronic spin, such as the nitrogen vacancy center in diamond, coupled to impurity nuclear spins in the crystal lattice, which are typically very sparse, such as the carbon-13 spin in diamond. So because of the sparsity, these nuclear spins are very weakly interacting with each other. And in addition to that, the electronic spin of the nitrogen vacancy center can be used to individually spectrally resolve these different nuclear spins and independently address them. And this means that each nuclear spin in the environment can be used as an independent quantum register, which can be used to store a quantum state. At the other end of this kind of spectrum, we have a regime that's epitomized by quantum dots, typically by indium gallium arsenide quantum dots, where the nuclear spin ensembles in these devices are typically very dense. And in addition to that, the electronic spin is highly delocalized, typically over about 10 or so nanometers. And this means that it homogeneously couples to about 10, if not 100,000 of these nuclear spins. And this makes quantum control of this kind of large nuclear spin ensemble a formidable experimental challenge. And indeed, realizing nuclear spin-based storage in these systems is as yet an unachieved challenge, an unachieved goal. Our system kind of realizes an intermediate regime between these two systems. So the spin bat that we work with, the vanadium in this yttrium orthovanadate crystal, is dense. And this is largely because of the isotopic purity of the vanadium. So by natural abundance, more than 99% of it is this vanadium-51 isotope. But in addition to that, the electronic spin of these rare earth ion atoms is highly localized. And this means that it interacts with only a very small environment of these vanadium spins, typically somewhere like around about 10 or fewer vanadium nuclear spins. And this means that we have a very confined, controllable many-body system, which is pretty much deterministic. So every single ytterbium ion will have an identical environment of these vanadium nuclear spins. And for all of these reasons, we think that this is quite an interesting regime to explore. So to give a little bit more detail.
Sorry, Andrei, that 99.8, that's a reference to how much variability there is in the environment from one electron spin to another. What does 99.8% mean?
Right. This is the natural abundant, in a naturally abundant vanadium sample, what percentage is this 51 isotope, which we're going to be using subsequently to realize the register. And so the fact that there's only a 0.2% probability of it being a different isotope means that in all likelihood, the environment of each of these ytterbium ions is essentially going to be identical.
Okay, thanks.
So generally speaking, the environment around these ytterbium ions consists of yttrium, oxygen, and vanadium atoms. And the reason we focus on vanadium is because it has the largest magnetic dipole moment of the three. And in addition to that, because it has this 51 isotope that I mentioned previously, has a nuclear spin of 7/2, This leads to it having a zero field electric quadrupole structure shown here on the right, which is generated by this quadratic type Hamiltonian. This leads to 4 doubly degenerate Z-directed eigenstates separated by 3 magnetic dipole allowed transitions, which I'm going to label A, B, and C. Critically, because of the quadratic Hamiltonian, these 3 transitions are non-degenerate, so they have different frequencies, and we're able to spectrally resolve and address them independently. We're going to be working with these 4 specific vanadium ions to form our register, and the reason for this is kind of twofold. So first of all, because of their position within the crystal lattice, it turns out that we can use the ytterbium to drive these magnetic dipole transitions between the energy levels. But also in addition to that, due to their proximity to the ytterbium atom, they experience a frozen core type detuning, where they experience a slight frequency shift of these transitions relative to the other vanadium spins. And I'll show some experimental results later which demonstrate this. All of the other vanadium atoms in the environment of the ytterbium, they form the bath, and this actually acts as a noise source which limits our ability to perform coherent control of the register. So there are kind of 2 main challenges in working with this system to realize a quantum register. So the first one is that the qubit transition that we're working with is a clock transition. So the ytterbium levels have no magnetic dipole moment. And this means that all of the secular interaction terms that you would be typically using to generate interactions are 0 to first order. However, the situation is actually a little bit worse than that, because the dominant second order interaction is actually stochastic and can't be used to realize coherent interaction between the ytterbium and the register. To give a little bit more detail on this process, the bath that I mentioned on the previous slide actually generates a mean field, which we're going to call the Overhauser field. And as these bath spins undergo flip-flops or T1 relaxation, this Overhauser field undergoes some kind of random evolution, time evolution, which is kind of quasi-static on fairly short timescales, but is fluctuating nevertheless. This Overhauser field then induces a magnetic dipole moment on the ytterbium, which is also randomized. And it's in fact this randomized dipole moment, which is then the dominant source of interaction with the register. And the interaction strength is actually then dictated by the strength of this Overhauser field. And because of the random nature, you can't actually use it to generate coherent gates. So this is kind of the first challenge. And the second challenge is actually related to the position of these vanadium ions. So because all of these 4 register spins are equidistant from the ytterbium, they have identical frequencies, and they also have an identical interaction strength. And this means that they're essentially indistinguishable regarding their interaction with the ytterbium. And therefore, we can't use a single vanadium spin to store quantum information. And we actually need to use the ensemble of spins to store information in some kind of collective state. We overcome both of these challenges using a novel experimental scheme, which I'll detail over the next few slides. And at the heart of this scheme is a new pulse sequence that we developed called ZanPol, which enables us using dynamical Hamiltonian engineering to generate a coherent spin-preserving interaction between the ytterbium and the vanadium spins. This is very similar to the pulse sequence, which was recently demonstrated. However, a key point of difference here is that it generates this polarizing interaction at 0 magnetic field using a clock transition, so using a magnetically insensitive transition. So this sequence, to give a bit more detail, consists of equidistant pi and pi on 2 pulses separated by a variable wait time, tau on 4, combined with a synchronously applied square wave RF magnetic field. When the pulse separation, when the sequence period is synchronized with the precession frequency of these vanadium spins, this omega j here, according to this resonance condition, then for odd integer k, the leading order interaction dynamics can be approximated by this time averaged Hamiltonian shown here on the right, which has the desired spin exchange or spin preserving form with an interaction strength which is dictated by this RF field amplitude. In addition to that, this sequence also exhibits even resonances. So this interaction here is generated when k is odd. When k is even, we also generate similar interactions, but with a strength which is dictated by the Overhauser field amplitude rather than this RF field amplitude. And so we really want to use only these odd k resonances to generate our interaction. The duration of this interaction is determined by the number of sequence repetitions m. And in addition to all of this, I just want to highlight that we designed the sequence to be robust against various sources of noise. So for instance, it extends the ytterbium coherence time, and it's also first order insensitive to pulse duration errors.
What
So,
what are the times? What are the timescales here? Like, how long does it take for this sequence?
right. So typically for the transitions that we're working with, the pulse separation here is about 0.5 microseconds. And the effective interaction strength we can generate is about 10 kilohertz or so. And so I'll explain in a few slides how we can use this to generate a swap gate with the register, but our typical swap gate time is about 50 microseconds.
Okay.
So we can use this spin exchange type interaction in the first stage of our protocol, and we use it to perform unidirectional transfer of the vanadium spin population, i.e., to polarize the vanadium spins into a specific one of these energy levels. We do this by repeatedly initializing the ytterbium into a specific state and then undergoing resonance spin exchange with one of these three magnetic dipole transitions. When we do this, we can shelve the vanadium population into this uppermost 7/2 level to realize this kind of polarized state, which we're going to call 0V. I mean, in fact, from now on, we're going to be adopting this spin down, spin up representation and operating within this kind of restricted two-level manifold of the vanadium spins. Once the vanadium register is polarized, we can actually use the same interaction to generate coherent spin exchange between the ytterbium and the vanadium register. We do this by preparing the ytterbium in the spin-up state and then undergoing this coherent population exchange, spin exchange interaction, whereby the spin excitation is transferred to the vanadium. But due to the symmetry of the interaction, the symmetry in the coupling strength to all four vanadium spins, this excitation is actually equally delocalized across all four vanadium register ions, thereby realizing this W-type state, which can also be called this kind of spin wave-like state. I also want to note that if we were to prepare the ytterbium in the spin down state, there would be no spin excitations in the system, and this spin exchange would then be forbidden. And in addition to that, this spin exchange interaction is enhanced, collectively enhanced by a factor proportional to the square root of the number of spins, in this case, the square root of 4. So this interaction, when you realize a full swap, a full spin exchange, a pi-Rabi oscillation, realizes a quantum swap gate. So if we prepare some arbitrary state on the ytterbium, arbitrary quantum state, and perform a swap, then we can transfer this state onto the vanadium register, where we're actually using this W-type state as a constituent of the register qubit basis. And then after some wait time, we can perform a second swap to transfer the state back onto the ytterbium. And this is really the storage scheme that we're going to use to realize this secondary qubit register. And I just want to mention, this is kind of a scheme which was first of all proposed in the context of quantum dots in this paper here. So moving on to kind of the experimental demonstrations of this protocol. Actually, maybe now is a good time to pause just quickly if anyone has any questions before we move on to the experimental section. I'll wait for
it. I probably misunderstood what you meant. You said that if the spin is down, nothing happens, but here something is happening for spin up or spin down.
Right. So actually, if you look at the initial state, if the ytterbium is in the spin down state and the vanadium is in this polarized state, then nothing happens. And so in your resulting state after the swap, that component of the state, spin down, all vanadiums down, is unchanged. However, in the case where the ytterbium started in the spin up state, the ytterbium will flip to the spin down state, but the vanadium will now enter into this W-type state where the spin excitation has been transferred. And that's how you do this kind of swap operation or the storage.
But is it a swap only if you prepare this particular state of the vanadium swings and not for a general state of the
absolutely correct
vanadium too? So it's not really a swap. I mean, usually when we speak of a swap, we imagine we've got two qubits and they change places, but this is for some fixed state of the vanadium manifold, right?
You're absolutely correct. So this is essentially assuming that you're operating in the single excitation basis, then it will operate as a swap in this limited basis. So if you start with a state which has more than one spin excitation, so let's say we had stored this state, and now we put the ytterbium into the spin up state rather than the spin down state and try to apply a swap, then there would be a certain probability that rather than going back to the original case, we would transfer a second excitation into the vanadium ensemble. And in that case, this scheme doesn't operate as we want it to. However, I'll show some results a little bit later where we can actually operate with a slightly different set of vanadium states, where this possibility of doing a second spin excitation is prevented. We didn't actually demonstrate in this work that we could do quantum storage in that scheme, but we actually used it to kind of characterize the collective enhancement of the spin exchange oscillations. But maybe we can have this discussion once I've shown those results, and then I can kind of explain how it enables this full quantum swap operation.
Anyway, for this particular preparation of the vanadium state, it loads the quantum state into the vanadium. Right.
It does, and then as long as when you want to retrieve it, you put the ytterbium back into the spin down state, it'll also retrieve it.
Okay.
Yeah. Okay, so the first thing we do experimentally is we use this sequence to perform spectroscopy of the vanadium environment to verify that we can indeed interact with these quadrupole levels with the magnetic dipole transitions of the vanadium. And we first of all actually do this with the RF field turned off. So what we do is we prepare the ytterbium in the spin down state, and we perform a Zanpol sequence with a variable interpulse separation, so variable frequency, and we see what's the probability of us flipping the ytterbium state. In other words, what's the probability of us interacting with the vanadium spin. And we see with the RF field off that we observe these even K resonances corresponding to interactions driven by the Overhauser field, these kind of stochastic interactions. However, when we turn on the RF field, we observe some additional odd K resonances are additionally activated, and these actually correspond to the coherent spin exchange that I mentioned previously. We can zoom in on this resonance here, which corresponds to the C transition of the vanadium of the vanadium ions, and we see that it exhibits this kind of split resonance structure. So we actually attribute these two peaks to two distinct ensembles of vanadium spins, the register and the bath that I mentioned previously. So this peak at about 1028 kilohertz, it actually agrees very well with previous studies of bulk yttrium orthovanadate measured using NMR. And we therefore postulate that this corresponds to a more distant ensemble of vanadium spins, which don't experience any kind of influence due to the ytterbium. However, this second peak, we postulate corresponds to the local register, which because of localized strain in the vicinity of the ytterbium, experiences a slightly frequency shifted quadrupole structure, and therefore becomes spectrally resolvable. The frequency difference between these two dips is about 37 kilohertz, and this gives you an idea for maybe how strongly we can interact with one of these ensembles without influencing the second ensemble. Once we've identified this C transition for the register, we can then polarize it, as I mentioned previously, by repeatedly initializing the ytterbium and undergoing resonance spin exchange. We do this at 991 kilohertz, and we follow this with a variable tau measurement sequence, a probe sequence, which is sensitive to the population in the spin-up level. And indeed, we see that we can achieve high efficiency polarization of this register C transition here, whilst leaving the bath transition at 1028 kilohertz essentially unperturbed. And this is kind of additional evidence that we're dealing with two distinct ensembles of vanadium spins. Based on this and also additional experiments, we estimate that we can get a polarization fidelity of our register of about 84%. With the vanadium register polarized, we can then initialize the ytterbium into the spin-up state and undergo these coherent spin exchange oscillations. And in fact, we do this first of all in the yellow trace, for the yellow case here with a fully unpolarized vanadium ensemble. And we see pretty much just exponential decay with almost no coherent population exchange. However, as we gradually increase the polarization, the degree of polarization of these vanadium spins going from yellow to red to blue, we observe an emergence of these coherent spin exchange oscillations. We can verify that these oscillations are indeed a resonant phenomenon by varying the detuning of our Zanpol sequence relative to the vanadium C transition frequency. And we observe this kind of characteristic Rabi type resonance. We also verify that when we initialize the ytterbium into the spin down state with no spin excitations in the system, these spin exchange oscillations are totally suppressed. And we also demonstrate in this inset that as we tune the RF field amplitude, we can linearly vary the interaction strength between the ytterbium and the vanadium ensemble. I mean, this really enables us to tune our quantum swap gate and optimize the fidelity. We also demonstrate that we do indeed observe this collective enhancement of the spin exchange frequency, and this is kind of a demonstration that we're preparing these W-type states. And we do this by performing an alternative initialization protocol, which prepares only a single spin in the C transition manifold. So to do this, we first of all polarize all vanadium spins into the 3/2 level, and then we perform a single spin excitation on the B transition, thereby preparing one spin in 5/2, before then measuring this, the exchange frequency on the C transition. And when we do this, we observe these spin exchange oscillations that occur at a reduced frequency relative to the 4-spin case that I showed previously. And the ratio in these oscillation frequencies is about 2, which corresponds to the square root of 4 type enhancement. And in fact, this is kind of what my response to John was kind of referring to, where once you have a single spin in this C transition manifold, you can actually now use this also as a quantum storage basis. But now, because you only have a single spin, you can't add additional spin excitations. And if you were to operate in this basis that I show here, then your swap gate would be really a quantum swap gate, like an entire swap gate. But for the rest of this talk, I'm actually going to be focusing on these collective type interactions using the 4-spin basis. So these oscillations, spin exchange oscillations that I showed here, are really just a demonstration of classical information exchange between the ytterbium and the vanadium. But really want to show that this is a quantum register. And to do this, we prepare a superposition state on the ytterbium. We swap that onto the vanadium spins. We wait for a variable time before swapping back onto the ytterbium and measuring in the X basis. While the state lives on the vanadium, it actually accumulates phase at the vanadium frequency, which is about 990 kilohertz. And indeed, we do observe oscillation in the ytterbium readout at this frequency. And by measuring the decay of these oscillations, we can extract a coherence time for a register of about 60 microseconds. And we can, in fact, understand this, this coherence time by considering the influence of 2 different sources of magnetic field noise on the system. The first of these is the nuclear Zeeman interaction of the vanadium register spins with the Overhauser field generated by the bath. And the second one, which turns out to be dominant, is actually the magnetic field generated by the induced ytterbium dipole moment. So I mentioned previously that this was a stochastic fluctuating dipole moment generated by the Overhauser field itself. But in fact, because of the proximity of the vanadium register to the ytterbium is actually acting to amplify that Overhauser field by a factor of about 3. And therefore, it's this noise source which dominates the decoherence of our vanadium register. We're going to call this, this kind of effective field generated by the ytterbium is called the night field. However, a nice aspect of this field is that we can control its sign by determining whether the ytterbium is in the 0 state or the 1 state, the spin down state or the spin up state. And this gives us a degree of control which lets us decouple from this field. Specifically, during the wait time, we apply periodic pi pulses to the ytterbium spin, each of which flips the sign of the night field and leads to cancellation of phase accumulated during successive free evolution periods. This is kind of a process similar to motional narrowing and leads to an extension of the vanadium register coherence time to about 230 microseconds. We can also decouple the vanadium spins directly from the Overhauser field itself by doing dynamical decoupling, whereby we apply a pair of vanadium pi pulses to the register during this wait time, and this leads to an extended coherence time of the register of about 760 microseconds. I'm kind of running out of time, but I just want to kind of briefly mention that in addition to using this register to store and retrieve quantum states, we can also use this protocol to prepare Bell states, and these are joint ytterbium-vanadium Bell states, using the same spin exchange interaction. Just rather than undergoing a pi Rabi oscillation, we undergo a pi on 2 oscillation. And in this case, we can prepare this psi plus type Bell state. I should also say, by the way, that preparing and measuring these kinds of Bell states is actually a critical part of the quantum repeater protocol. So we can prepare this kind of psi plus type Bell state. But then once prepared, if we undergo just free evolution, the component of the state where the spin excitation lives on the vanadium will acquire phase at the vanadium C transition frequency when you're in an ytterbium rotating frame. And this means that the psi plus Bell state will actually undergo parity oscillations with its parity conjugate state, the psi minus Bell state. And we can read out these oscillations by applying a second square root of swap gate, which maps the psi plus and psi minus Bell states to these two quantum states, whereby we can then measure the Ytterbium state as a proxy for this initial state parity. When we do this, we observe clear oscillations of this Bell state parity with a decay time of about 8.5 microseconds, which we can actually understand is now being limited by the Ytterbium Ramsey coherence time. And we can actually extend this coherence time by applying an XY decoupling sequence to the Ytterbium, which not only extends the Ytterbium coherence time to about 16 milliseconds, but additionally, because we're applying successive pi pulses, leads to this kind of motional narrowing type effect for the vanadium that I mentioned previously. And so now we measure an extended Bell state coherence time of about 240 microseconds, which is now limited by the vanadium Ramsey coherence time. I just want to mention also that we can measure these states in the population basis, and this enables us to reconstruct the Ytterbium-vanadium joint density matrix in this kind of restricted basis corresponding to these 6 elements. In this process, we've performed a correction for the fidelity of our readout. And in this case, we can estimate a preparation fidelity of about 76%. And this is limited by the contrast of our spin exchange oscillations that I showed previously. And at the moment, even though we don't know exactly what's limiting this, we have a number of hypotheses. So we think it could be caused by heating induced by the RF field that we're applying. It could be caused by some vanadium-vanadium interactions, which we haven't been considering yet in our model. For instance, exchange interactions. It could be caused by some excess dephasing on the Ytterbium, or a certain element of it could be also caused by incomplete polarization of the vanadium spins. We also demonstrate that this register is reproducible by measuring the 3 different Ytterbium ions inside our optical cavity, ion 1, ion 2, and ion 3. And we measure both the C transition spectrum, the spin exchange dynamics, and also the motionally narrowed Ramsey coherence time for all 3 of these ions. I just want to emphasize that in all of these cases, the aspects of the sequence related to the vanadium ion control are actually identical. And in all of these, we observe identical transition frequencies for the vanadium, pretty much identical spin exchange oscillations, and very similar coherence times. It really demonstrates the deterministic nature of this register, which is kind of a critical demonstration for the scalability of this system. Finally, and very quickly, I just want to kind of mention that in addition to these kind of W-type states that I've talked about, we're also working towards realizing other quantum states of this vanadium ensemble. So for instance, more recently, we've been looking at preparing GHZ-type states, which kind of have a significant importance in quantum metrology. And these states can be prepared from the vanadium, from the initially polarized vanadium ensemble using a combination of controlled rotations on the vanadium and local qubit gates on the Ytterbium. And these are kind of these joint Ytterbium-vanadium GHZ states. So not only do you have the vanadium in this kind of spin up state, but also the Ytterbium is in 0G. So much like the Bell states that I showed a couple of slides ago, under free evolution, this state will undergo parity oscillations. But unlike the single excitation manifold, these oscillations now occur at an enhanced rate, corresponding to 4 times the C transition frequency. And we can use a very similar sequence to read out these parity oscillations. And we do indeed observe an oscillation at about 4 megahertz. We can do a Fourier transform. And indeed, we see this for this oscillation component that occurs at 4 times the base C transition frequency with a sharp cutoff afterwards. However, we are also measuring lower harmonics of the C transition frequency, and we can understand these as being caused by incomplete polarization of our vanadium ensemble, leading to imperfect preparation of these GHZ states.
Is this plot real data?
This is real data. Yep.
Cool.
In conclusion, we think that this 171 Ytterbium doped into yttrium orthovanadate is a kind of very versatile platform for realizing optical quantum networks. In previous work, we demonstrated that we could achieve a very stable optical interface to these qubits with very long or very good spin coherence times and high fidelity single qubit gates. And in this work that I've talked about today, we've demonstrated that we can realize a secondary quantum register using spin wave-like excitations of these nearby vanadium ions, with quantum storage with memory times of up to about 760 microseconds. In addition to that, we've demonstrated that we can prepare and measure both Bell states using this kind of single excitation manifold and also these GHZ type states. And also this register is reproducible and deterministic across multiple ytterbium atoms that we've measured. Moving forward, we're interested in using this register to actually realize multi-qubit storage for our ytterbium atoms. We're interested in using pairs of ytterbium atoms in different cavities to demonstrate remote ytterbium entanglement. We're also interested in using very dense ensembles of these ytterbium ions to realize bulk polarization of the vanadium nuclear spins. And this is actually one kind of nice aspect of the rare earth ion system, where even as you go to very high doping concentrations, the inhomogeneous line widths of these transitions remain very narrow. And we believe that this means that it will be able to achieve very high fidelity control of these dense ytterbium ensembles, which we can then use to perform some kind of hyperpolarization of the yttrium or the vanadate crystal. And then finally, I think that this kind of provides a more general framework for working with these kind of very dense nuclear spin hosts. And this potentially opens the door to exploring additional materials for quantum information applications. So with that, I'd like to thank you for listening to my talk. And I'd also like to specifically acknowledge Chunru, who's kind of helped me a lot with some of these experiments in the lab, and Junhee, who was really instrumental in developing a lot of the experimental protocols that we used in the discussion today, and obviously my advisor, Andrei Faraon. So thanks for listening. I'd be happy to take any questions.
All right, thank you very much, Andrei. That was a great talk. Are there any questions?
How are you going to establish the ytterbium entanglement?
So probably using a Barrett-Cock type protocol. So essentially emitting indistinguishable photons from a pair of these ytterbium atoms and then entangling them or interfering them on a beam splitter. We're probably going to start by actually doing this with two atoms in a single cavity, and then at two different frequencies, and then frequency shifting one of the photons and interfering them. But then if that works, we'll move to two cavities with two ytterbium atoms.
So I have one that I was wondering about. You showed the slide showing a few different ions, and I was curious how you address the different ions. Are they in the same cavity, or are these different cavities, or?
Yeah, so these are actually all in the same cavity. And this is actually stuff I didn't really talk about because it was kind of more like preliminary work setting up the platform. But essentially, within one of these cavities, we typically have somewhere on the order of about 20 to 30 ions. And this is just because we work with crystals which have some kind of small concentration of these ytterbium atoms, and that corresponds to this number in our cavity. But then what enables us to address a single atom is actually the fact that based on the local environment, the strain environment in the crystal, each of these ytterbium atoms will have a slightly different frequency. And this is kind of your inhomogeneous distribution. And so primarily this inhomogeneity we leverage in the optical domain, so we can optically spectrally address different atoms and only work with a single one.
You had a list of limitations or potential limitations on the Bell state fidelity.
Yes.
How do you feel about the prospects for mitigating those and getting substantial improvement?
So I think heating, one way that we could win on heating is we could switch to using superconducting waveguides in our device because we operated zero magnetic field. I think that this is kind of a fairly straightforward way to mitigate that. The excess ytterbium dephasing, we actually at the moment think that it could be limited by, so I didn't really go into details of this, but it's quite important in our scheme that the RF field that we apply is a perfect square wave. If it isn't, then this combination of like the detuning induced by the RF field with the Overhauser field can actually cause dephasing still. And so we have some suspicion that actually by the time this RF field gets into our helium-3 fridge, like to the device, it's no longer a perfect square wave. And so doing an optimization on the shape of this RF field, I think, will likely help us mitigate some of the excess Ytterbium dephasing. As far as the vanadium-vanadium interactions are concerned, at the moment, we don't understand the interactions. Like we considered kind of two main interactions in our simulations. One was direct nuclear magnetic dipole-dipole interactions between the vanadium spins, but these are very slow. They occur typically on the order of like a few hertz. But there are also kind of enhanced interactions which occur by virtue of the ytterbium mediating the interaction between the two vanadium spins, almost like a three-body type interaction. Those occur a bit faster at about 100 hertz, but are still not fast enough to explain the decay and oscillation contrast that we see. So I think we would need to, first of all, understand kind of the Hamiltonian generating these interactions if they are the main limiting factor. But then we can start thinking about designing some robustness into our pulse sequence, which can perhaps decouple some of these interactions, which might be possible if we included maybe some kind of pi pulses on the vanadium spins or some additional degree of vanadium control to enable this decoupling. As for the incomplete polarization, this is probably the one that we have like the best idea of. So both these GHZ spectrum that you see here, and also by fitting to the spin exchange oscillations that I showed here, give us a pretty good idea of where our population is distributed within these vanadium energy levels. So at the moment, I think our estimate is that we have about 84% in this top level, we have about 10% in this level, and we have about 6% distributed between these two levels. And so I think that that's probably the one where we certainly can measure the population pretty well. And I think then we can either try to improve the fidelity of our polarization sequences, or perhaps consider using other polarization methods. So I guess an aspect of the polarization is that it doesn't need to be coherent. You can achieve polarization even if you're using kind of interaction driven by this randomized Overhauser field. And so you could potentially use Hartmann-Hahn sequences or other more established polarization sequences to do this without the necessity for it to be coherent. And maybe some of those would lead to higher efficiency polarization. So I think those are like our main approaches that we would take for addressing these four different issues.
And it's unclear at this time which of these is the most serious limitation.
Yeah, we kind of tried for each of these, we tried things to identify whether it independently was its own was a limitation. So for instance, I think for the excess ytterbium dephasing, we tried to adjust what we thought, we tried to make the dephasing worse and saw it would have an effect. For the heating, we tried to increase the RF amplitude and see if it would have an effect. And none of these independently have a dramatic effect. And so I think likely we're actually limited by some combination of them, which as yet we've not fully determined exactly which combination of these are our limiting factor.
All right, thanks.
More questions?
Hey, Andre, nice talk. I just had a quick question about, I guess, the next steps.
Oh, yeah.
So I saw you mentioned new material platforms like lithium niobate in your last slide. And what would be the advantages of moving to those platforms, and what would be some of the challenges associated with it?
Right. So I think like the motivation here is kind of that rare earth ions are pretty like, they don't really mind what host you put them into. So you can put ytterbium into a range of different hosts and it'll have very similar optical transitions, like in terms of the frequencies, etc. And so this kind of really gives you a bit of a playground to try to kind of put these ions into different hosts and see if you get some promising properties that you maybe don't get in the current platform. So from, let's say, the nuclear spin perspective, I think one interesting aspect of this would be that depending on exactly the crystal geometry, you could get a different environment of these nuclear spins. Maybe you can realize registers with larger, fewer numbers of spins. But also actually there's kind of like a small limitation to this platform, which I haven't really talked about in this talk, where even though these 4 register spins that we work with, even though these are the 4 register spins that we work with, the 2 vanadium spins which are closest to the ytterbium are actually this one and this one, which are closer than the register. And the reason that they don't form part of the register is because of their position, because they're directly above and below the ytterbium. Their interaction with the ytterbium is actually only Ising-like. And this means that we can't use the ytterbium to drive transitions between the quadrupole levels. So when we kind of set off in this project, we thought that like by controlling the nuclear spin environment, we could actually improve the coherence of the ytterbium itself. But because we weren't able to interact with these 2 nearest spins, which were determining primarily the ytterbium coherence, we weren't really able to improve the ytterbium coherence at all. And so by moving to different platforms where you can actually control the entirety of the nuclear spin environment local to the ytterbium, this potentially then gives you a route towards using these kind of techniques to also improve the coherence of your qubit. Specifically for lithium niobate, I think a nice reason to explore it would be that you have a whole host of nonlinear properties that you could also explore. So for instance, one additional potential downside to the current platform is that Ytterbium emits at 980 nanometers, which isn't within this low loss kind of transmission region of optical fibers. So if you could use lithium niobate and then perhaps even use the nonlinearities to do up conversion to 1550 nanometers in the same device, or even like in the same kind of photonic platform, I think that would be a very powerful demonstration. That's maybe like a motivation for lithium niobate specifically.
Awesome, thanks.
So, Andrei, can you compare this platform to, for example, like quantum networking with MV centers? Like, if you were to have, let's say, your dream device made in this material, how would it compare to a network in what has been demonstrated so far with MV centers?
Right. So I think that that question is like, at the moment, based on like the current device, I don't think we would be able to outperform current state-of-the-art nitrogen vacancy center experiments. The tricky thing, I think, is that typically, sorry, I don't know why I'm on this slide. Typically, the schemes that you can use for doing 2-qubit entanglement have some inherent trade-off between the rate with which you can generate the entanglement and the fidelity of the entangled state. And so typically the reason for this trade-off is because the photons that are emitted by your ytterbium atoms or nitrogen vacancy centers aren't perfectly indistinguishable. And therefore you can use certain tricks such as post-selection, which increase the fidelity of your entangled state generation at the cost of the rate with which you can do this entanglement. And I think at the moment we don't have a thorough enough understanding of the optical coherence properties of the ytterbium to say kind of with concreteness exactly what the optimal balance between these two will be, and therefore how we will compare in that case with the nitrogen vacancy platform. But I think if I remember correctly, based on some back of the envelope calculations, using this current device, we should be able to get an entanglement rate of maybe half a hertz or something like that. And I think that the entangled state fidelities should be, they're not great. They're maybe somewhere on the order of about 60%, but that's condition that, like, that's, I think, assuming no post-selection. And so once we understand the spectral diffusion properties of the ytterbium in more detail and know how to mitigate those, that fidelity will go up.
Could you remind us what the corresponding numbers are now for NVs?
I'm not sure I have those off the top of my head for their most recent results. I'm sorry.
So are you talking about like two-node quantum network or three-node?
I'm talking about entanglement, the rate of entanglement generation and the fidelity of the entangled pairs. Yeah.
Andrei, were you talking about were you comparing with a three-node or a two-node?
We could do either.
Yeah, because I think with the three-node, I think that is their entanglement is like below a hertz, right? I think it's like
The 3-node entanglement rate, I think, is below a hertz, but the 2-node entanglement rate, was it?
like it was tens of hertz.
It is tens of hertz. Yeah, exactly.
Okay. But what about the
All right.
fidelity? I guess I thought they had much higher fidelity in tangled pairs than the NVs, no? Then you're, yeah. Oh, okay.
You can double check and get back to you.
I can look that up. Thanks.
All right. Well, thank you very much, everyone, for coming. Thank you, Andrei, for a great talk. Here, I'll just stop the recording.
Actually, it's